if you remember last time we introduced this idea of normal extension. So remember, a normal extension is one that's algebraic, and for each polynomial, if it starts to split, right, if it has a root in the big field, then it splits entirely. So it sort of finishes the job. If it gets started splitting, then it finishes the job. That's what it means to be a normal extension. Now, and then we proved a theorem, that was theorem, I guess it was 3.1, right, that characterized normal extensions in terms of a splitting field. So it was normal if and only if it was the splitting field for some collection of polynomials. That's really the general statement, but more often than not, we won't need it to be quite that general. And so here's this corollary is actually one that we'll rely on more often. So corollary 3.2, and this is in the case that we have a finite extension. So let's let L over K be finite. Then L over K is normal if and only if L is the splitting field for some polynomial, a single polynomial, let's say for some f in k bracket x. Oh, for whatever reason, why did I use g? You know what, in my proof I used g, so let me call that polynomial g here in the statement also. Okay, so to prove this, and the proof technique is going to look kind of familiar. So in the forward direction, first let's let alpha 1 up through alpha n in L be such that L is equal to k adjoin alpha 1 up through alpha n, right? It's a finite extension, so we know that L can be expressed in this way. Now, and we saw this in the previous proof, so let's define our function g equal to, and it'll just be the product, m alpha 1, m alpha 2 up through m sub alpha n, right? So just take the product of the minimal polynomials of each of those alphas. Now, since g of alpha 1 is equal to 0, using the assumption that it's normal, we know that it's going to split completely over L. So since g of alpha 1 is equal to 0, we have that g splits over L. Sorry, I just got lost here. Now, since the splitting field for G over K is, well, so how would you get the splitting field? It's K adjoin, let's say, R, where R is the set of roots of G. It follows that, so what I want to say here, it follows that L is the splitting field for what am I doing? L is the splitting field for G over K. So okay, so let me make sense of this. So we know that G splits over L. We know that this one is the splitting field for G. But then this one, how do I, yeah, now L is contained in that one right there, and so then they have to be equal, right? So L is equal to this right here. In the reverse direction, now this is going to follow immediately from our previous theorem, right? If L is the splitting field for a single polynomial, well, just write the set capital S equal to, or let S be the set consisting of this single polynomial. This follows immediately. From 3.1, letting S equal the set containing just little g. All right, so this tells us that in the case that we've got a finite extension, we can decide whether it's normal or not by just deciding whether it's the splitting field for some polynomial. So as an example then, and I showed this example previously and said, well, we'll be able to show this a little later. And so now, right, Q adjoined root 2 over Q is normal. Now, why is that? Because Q adjoin root 2 is the splitting field for the polynomial Q, x squared minus 2 in Q bracket x. Right? So here we know that we've got a finite extension, and so to say that it's normal, all we need to do is identify a polynomial for which, right, the bigger field, the extension field, is a splitting field. Okay, so now another definition. So let's start off with an algebraic extension. So let's let L over K be algebraic. Now, an extension of L, so an extension N over L is a normal closure for L over K if, well, so what we want is for our extension N over K to be normal and to be minimal in some sense, right? So two things. First, we want N over K, so this is normal. And second, if we have this situation here, so it's going to be K lives in L, contained in, do I want to use M? Yeah, M contained in N, and M over K is normal, then M has to equal N. So a normal closure, right? You start off with an algebraic extension. A normal closure is an extension of the extension that gives us a normal extension. So we're going to build L out. So the idea is if you start off with this extension, maybe this extension is not normal. And so what you do is you expand L just the right amount to give yourself now a normal extension, and it's going to be the smallest, right? In the sense that if we have anything small, supposedly smaller, or I guess we'd say this, you can't have anybody strictly smaller than N that yields a normal extension for K. Now, it's not automatically clear that such an object exists, right? That you can just build out your original extension and get it to be normal. But this corollary 3.3 goes like this. If we start off with a finite extension, then L over K has a normal closure N. Now, okay, technically it's the extension that's normal closure, so I guess I should say L has a normal closure N over L, and it turns out that it's a finite extension, and, or let's say with N over L having finite degree. Okay, so for the proof, let's see what we need to do. Well, first of all, we know that we've got a finite extension, which means that L can be expressed as K adjoins some finite collection of alphas. So let's write L equal to K adjoin alpha 1 up through alpha n, where each alpha I is in L. So, right, so we can do that because we have a finite extension. And then it's going to be the same trick that we did before. We're going to define G to be the product of the minimal polynomials of alpha 1 up through alpha n. So let's say, and define little g equal to m sub alpha 1 up through m sub alpha n. Now the splitting field for G over L, right? So do I want G over, yeah, G over L. So the splitting field say N for G over L. This is a normal extension. So this gives us, this is a normal, let's say this better, gives us a normal extension. N over L by our last theorem, or corollary, so by corollary 3.2. Now, we know exactly who N is. N is L adjoin all the roots of G. So since N equals L adjoin capital R, where R is the set of roots, of G. Oh, and each element of R is algebraic over L. We know that N over L is algebraic. So N over L is algebraic. That's, I don't know, that's a theorem from way back. It's corollary 1.8. Let me see. Each element in Yeah. Ah, right. And so now what do we have? We have a, what do we have? We have, oh, right. Okay. So we have an algebraic extension expressed as an extension using a finite number of algebraic elements right here. And so what that tells us then is that the degree of the extension is finite. So by, I think it's 1.7, by by 1.7 theorem. Sorry, I got distracted here. By theorem 1.7, the degree of the extension is finite. The next of our corollaries, so this would be corollary 3.4, if L over K is normal, L over K is normal, and we have somebody in between K contained in M, contained in L, then L over M is normal. And so the proof so let's see, we know that L over K is normal. So let's let S in K bracket X be such that L is a splitting field for a splitting field for S over K. We know that's what it means to be normal, or that's equivalent to being normal by our theorem 3.1. All right, so this is by 3.1. So now, if we viewing S as sitting in, as a collection of polynomials, right? Since K sits inside M, we can think of S as a collection of polynomials whose coefficients are in M. So viewing it this way, the result follows. All right, so now L is a splitting field for the set S over M. So the result follows. Now, one thing I guess I could say this is a warning, or one thing to be aware of. So look at how this happens, right? If we started off with a normal extension, L over K, then L over M is normal. However, M over K is not necessarily normal. So let's say note, if L over K is normal and K contained in M contained in L, then M over K is not necessarily normal. Right, L over M is, M over K is not. And so let me give you an example. So as an example, let's look at the polynomial x cubed minus 2, right? So x cubed minus 2 has roots. Well, okay, of course, there's the cube root of 2. And then there's the complex ones, and those are going to be, let me write them as omega times cube root of 2 and omega squared times cube root of 2, where omega is a third root of unity, right? So where w equals e to the 2 pi I over 3. Now, it follows that our extension, if you do q adjoin, and so it's just going to be we're going to need cube root of 2, and we're going to need omega. This is our splitting field. It follows that this extension is normal. But as we saw before, so let's say and, so we have this. We have this inclusion here, so it's going to go q contained in q adjoin cube root of 2 contained in q adjoin cube root of 2 and omega. So we know this extension right here is going to be normal by our previous corollary, but we saw earlier that this extension right here, this was an example from last time, this is not normal. Okay. So then the question becomes, right? So if we start off with L over K normal, we know that this extension right there is normal. This one is not necessarily normal. And so then the question becomes, when is it normal? This next theorem, and this is really a curious statement here, but it's going to actually characterize when the intermediate extension over K is normal. So this is theorem 3.5. So let's let L over K be a finite normal extension. And let's say that we have this intermediate field, and suppose that we have K contained in M contained in L. Now, the following are equivalent. And so there's going to be three statements here. Okay, so the first part, M over K, is normal. The second one, if we have an automorphism of L, so if sigma from L to L is an automorphism that fixes K, then sigma of M is contained in M. And then the third statement, if sigma from L to L is an automorphism, that fixes K, then sigma of M is equal to M. So, I mean, this is sort of unexpected, I guess. The automorphisms suddenly become involved here, right? And so, normal is equivalent to every automorphism that fixes K takes M inside M, and then, even stronger, right, an automorphism that fixes K takes M to M. Okay, so we'll just sort of go in order here. So first, we have to prove that 1 implies 2, right? So we'll assume that our extension is normal, and then we want to look at automorphisms. Let's assume M over K is normal, and let sigma from L to L be an automorphism that fixes K. All right, so now what do I need to do? I need to take an element of M, apply sigma to it, and show that it lives in M. So let's call it alpha. So let's pick alpha in M. Now, we know that L over K is algebraic, and so, right, this alpha lives in L, so the minimal polynomial is a polynomial in K bracket X. So since L over K is algebraic, the minimal polynomial for alpha exists inside K bracket X. So now, so let's look at so what do I do? I want to do M sub alpha of, whoa, what am I doing here? M sub alpha of, sigma of alpha. So we'll say now, M sub alpha of sigma of alpha. So what do we do? Well, we just need to crank this thing out. You know what? I need to write out the polynomial first. Sorry. So let's write M sub alpha equal to K sub 0 plus K1x plus dot 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 plus K sub n x to the n. So then M sub alpha of sigma of alpha. Okay, what that's going to be is, well, it'll be K0 plus K1 times sigma of alpha plus dot 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 plus K sub n, sigma of alpha raised to the n. Fine. But sigma is an automorphism that fixes K, which means that K0 is equal to sigma of K0. K1 is equal to sigma of K1, and so on. So this is sigma of K0 plus sigma of K1, sigma alpha, plus dot dot dot, plus sigma Kn, sigma of alpha to the n. And then we can combine it all in, you know, we've got a homomorphism. So this is sigma of K0 of K0 plus K1 alpha plus blah 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 plus Kn alpha n But that is sigma of m sub alpha of alpha, which was sigma of 0, which is 0. In other words, sigma of alpha is also a root of a minimal polynomial. Fine. Okay. So what? So since, right? Okay. So what do we know? We know that sigma of alpha is a root of a polynomial, and then we know that our extension is normal. So when it starts to split, it has to split completely, which means that all of the roots have to live inside M. So since M over K is normal, we conclude that sigma of alpha is an element of M. Right? All the roots have to live in M so that you can split over M. Okay, so what does that do? That gives us containment, so therefore sigma of M is contained in M. All right, so that proves 1 implies 2. Now let's do 2 implies 3. So now what we need to do is get equality. All right, so we're going to assume containment. So 2 implies 3. So assume that whenever sigma from L to L is an automorphism that fixes K, we have sigma of M contained in M. And you know, I should point out, we have this idea of fixing K, the coefficients of your polynomials, and you can see in the proof why that's useful, right? It allowed us essentially to interchange the behavior of M, or it interchanged the action of M and sigma, right? Over here, we had M sub alpha of sigma. Here, we have sigma of M sub alpha, right? So this idea of fixing K, having an automorphism that fixes K, allows us to do some nice arithmetic. Okay, so what am I trying to do now? I want to show that we have equality. Okay, oh, I like this. I haven't seen this proof for a while, so let me see. Okay, so then, let's say it like this. So then, sigma of x plus y is equal to sigma of x, sigma of x plus sigma of y. This is just the fact that it's a homomorphism, so for all x and y in M, and sigma of kx is equal to, well, it's sigma of k times sigma of x, which is equal to k times sigma of x for all x in M. In other words, sigma behaves exactly as a linear transformation does. And there is the other key aspect, or crucial, interesting aspect of being an automorphism that fixes K. That means that viewing our fields as vector space, as a vector space over K, we get that the automorphism, or the homomorphisms, the monomorphisms, behave as linear transformations. So let's say it like this. Oh, and I should have said for all and for all K in K. So now, viewing sigma from Oh, did I want to say? You know what? Sorry, I screwed one thing up here, right? Our domain and codomain is L. So these M's right here, whoops, those should both be L's. So viewing sigma from L to L as a vector space isomorphism, right? We know that it's one-to-one and onto, and now we can think of it as a vector, as a linear transformation. What do we know? We know that sigma has to preserve the dimension of subspaces, right? Isomorphisms preserve dimension. We have that the degree of sigma of m over k has to equal the degree of m over k. And so you can just say isomorphisms preserve dimension of subspaces. Therefore, sigma of m equals m. Oh, now you know. Sorry, I'm a little sloppy here. Oh, so let's say it this way: since, of course, that doesn't mean that they have to be equal, but the point is that we also have. I didn't use this fact right here, right? They have the same dimension, and if one is contained in the other, then they need to be equal, right? So since, sorry, that was crucial there. Since sigma m is contained in m, we have that they have to be equal. Sigma of m equals m. Right? If you have the same dimension and you're contained inside, then you have to be equal. Okay, so now the last step, we need to do 3 implies 1. And so, so now what we need to do is we need to say, assume that if sigma from L to L is an automorphism that fixes K, then sigma of m equals m. Okay, and now we want to show that m over k is normal. So since we've assumed that the degree of the extension L over K is finite, we have that the degree of M over K is finite as well. That's just Tower law. Therefore, the extension M over K is algebraic. That's like theorem, I want to say 1.7, is that right? Yep. Right, finite extensions are always algebraic. Okay, so now what we need to do is choose an irreducible polynomial over K that has a root in M, and we need to show that that polynomial splits over M. So, so now let f in K bracket x be irreducible, and let alpha in M be such that f of alpha equals 0. Now, as before, so I chose an irreducible polynomial, Remember that this is a constant multiple of the minimal polynomial. So once again, it suffices to show that m sub alpha splits over m. So it suffices to show that m sub alpha splits over capital N. All right. Now, we know that L over K is normal. And so we know that M sub alpha splits over L. So since L over K is normal and alpha is in L, we have that M sub alpha splits over L. So L definitely contains all the roots of M sub alpha. So let's choose another one. So let's pick, pick a root beta not equal to alpha of M sub alpha, right? Now we know that beta lives in L. We need to show that beta lives in M. So we show that beta is in M. Okay. So we're going to do a theorem 2.5 kind of thing. Our favorite theorem. So let's let the identity map. So let's let I from K to K be the identity. Now, since I of M sub alpha equals M of beta equals equals M beta of beta, which equals 0. Now we can apply theorem 2.5, so there exists an isomorphism J. Actually, I should just say, well, it's an extension. J from K adjoin alpha to K adjoin beta, such that J restricted to K equals the identity and J of alpha equals beta. This is, that's theorem 2.5. Okay, so now the next piece of the puzzle since L over K is a finite normal extension, right, okay, so since L over K is a finite normal extension, by, let's see, our theorem is, or corollary 3.2, there's some polynomial in K bracket X for which L is the splitting field. So there exists G in K bracket X such that L is the splitting field. For G over K. Oh, and of course, J fixes K, so we know that J of G equals G. So since J fixes K, we have that J of G equals G. Fine. Now, so now we need to remember our splitting field extension theorem. That's corollary 2.8, so that's what I want to apply here. So now L is, it's also the splitting field, so it is the splitting field for G over K adjoint alpha, and of course, so L is the splitting field for J of G, which is G over K adjoint beta. And let me draw the diagram just to kind of show you, or so just so we can keep our head straight. So we have the identity here. We have K adjoint alpha, K adjoint beta. I know my head's probably in the way, but I'll get out of the way in a second. That's J. Inclusions going down. And then we have L and L. Right, they're also inclusions. And then our splitting field isomorphism theorem, or splitting field extension theorem, that's 2.8, is going to give us an isomorphism from L to L. Right, we're all set up right here. So by corollary 2.8, there exists, and so it's an isomorphism from L to L. So let's call it an automorphism. So there exists an automorphism sigma from L to L. We know that it's going to fix, or it extends J, which means that it fixes K. So it's an automorphism. So we can say and. Since sigma restricted to K adjoint alpha equals J, in fact, I can say it this way: since sigma restricted to K is equal to J restricted to K, which equals I, we have that sigma fixes K. Now, what am I trying to do? I want to show, my goal is to show that beta lives in M, right? We know that beta lives in L. So now, since alpha is in M, we see that, so this is going to be beta, which equals J applied to alpha, which is equal to sigma applied to alpha. And we know that sigma, anybody in M gets taken to M, and so this is an element of sigma of M, which is equal to M. So beta lives in M. That's what we need. That's another tough proof. You know, you can see I don't have these memorized, right? These are intricate proofs, right? I hope that you can follow along and see the significance of each of these things, right? Fixing K has now become important. These extension theorems have become important, right? The pieces are starting to come together. This is the end of chapter 3. We're going to have another chapter. Chapter 4 comes up next. Of course, we're here. Well, anyways, there's one more piece of the puzzle, and then we can actually start doing Galois theory. Right? So we'll see you next time.